Assalamu alaikum. Today's topic is LOCI in 2 dimensions and in 3 dimensions, the basics. First and foremost, we need to know what LOCI is. So please kindly write down the definition. LOCI, the locus of a variable point can be defined as sets of points which satisfy certain given conditions. Certain given conditions. Now, according to this definition, first of all, you need to know what a variable point is. You see, when you talk in 2 dimensions, you talk about x-axis and the y-axis. This is called the 2 dimensions. In 2 dimensions, you talk about circles, you talk about rectangles, you talk about squares, you talk about distances, you talk about constructions. So everything that you see in 2 dimensions is something that's not touchable in real life. It's not touchable in real life. So it basically means something that is a circle. It's not touchable. Do not confuse yourself with a sphere. The sphere is 3 dimensional. The sphere is 3 dimensional. According to the syllabus, locus and construction requires certain given conditions and you need to be following them. We are dealing with 2 dimension loci at the moment, and the 2 dimension loci requires you to understand what possible solutions are there. Let's take, for instance, number one. Number one. Okay. Let's write the theory down. The locus of a variable point P. We're not going to take P as a variable point. That means it can vary, it can be placed in some position. Is which variable point P, which is at a constant distance R from a fixed point O is. Now, this is where we stop writing. Let us understand number one. Okay. So I'll allow you to write till here. We're going to come back to board number one again. Okay. I'm going to stop till here because the solution needs to be understood. The locus of a variable point P which is at a constant distance. Constant distance. The variable point P, constant distance from a fixed point O. Constant distance from a fixed point. So if I take this point O It's at a constant distance, R. So P could be here, yes or no? This is one possible position of P. But P could also be here. So when I start at the same distance R, P could be here. It could be P dash. Same distance P could be here, P dash. Same distance P could be here, P double triple dash, P4 dash, P5 dash, or fifth P. P1, P2, P3, P4, P5. When I start connecting these P's, what am I getting? A circle. Now remember, this is fixed distance R. It's a fixed distance R from a fixed point O. Now O is the center of the circle that has been formulated. So when they ask you what is loci, you're going to say possible positions of this point. The locus of a variable point P, which is at a constant distance. Constant distance, this is the constant distance. This is the constant distance. It turns out to be the radii of the circle. The radius of the circle, the radius of the circle. So how do you describe it? The locus of a variable point P, which is at a constant distance R from a fixed point O, is a circle with center O and radius R. Is a circle with center O and radius R. This is the first one, and after you write this complete answer, do not forget to draw a circle. I will give you another example which is much better, which is better than this one. Copy this. So we understand the first one, the locus of variable point P, which is a constant distance R from fixed point O, is a circle. You must draw the circle here. You must draw the circle. Draw full perfect circle. Take your compass and draw a circle. Now, I will be drawing a circle because of my experience. My circle will be almost perfect. Okay. Is that clear? This is your point P, this is your point P dash, be another point P dash here, another point. So locus is a theory question and also a practical drawing question. Everybody here sitting here, if you've crossed the age of 13 or 12, you know how to make a circle with a compass. Yes, of course. Correct? It's a constant distance R from a fixed point O is a circle. Is a circle. Now, giving you an example of this would be a practical day-on-day example. Would be, let's take for instance, you go to the villages, and they have these um, rods, and they have this tube well. Of course, some villages did not have electricity, so they have this little animal ox or something that walks around in its own way around a fixed point. It walks around. Okay, it is walking around in a fixed way, and it runs a tube well. It's called a manual tube well. They're able to pull water out from the well by using it in a circular way. Now, imagine similar an example would be that if I had a rod, a metal rod, fixed to, say, a prisoner, or say to another person here, and or to an animal, and there is grass all over here, where can that animal eat the grass? Only in this circular position. Okay? However, if it was not a fixed rod, then the animal would be able to eat all the food in this circular area. So don't restrict your thinking. Depends on the condition. If the rod is fixed, like in the question we gave you, a fixed distance r, oh, okay, then it's a circumference of a circle. Circumference of a circle. Okay? Keep your logic open. It's a circumference of a circle if it's a fixed distance r. But if it's not a fixed distance r and it's a maximum distance r, then that animal can eat all the grass in this shaded region. Is that clear? All around the circumference, but the entire area of the circle. So understand and be able to differentiate the two things. If they ask you a constant distance r, then it's a circumference of a circle. If they say a region around a constant distance r, then automatically is the area of the entire circle, involving the circumference as well, including the circumference as well. Okay, so that was number one. We understand this concept really well. Please make a small circle with a compass and do it. Thank you. Board number 3. Locus number 2. The locus of a variable point. Now again, we're using the variable point concept. Okay. The variable point P, which is at a constant distance r from a straight line AB is. Okay. Now, before we go ahead, you should be able to copy this till here while you're taking advantage of this lecture. Remember one thing, you need to start writing when I'm writing and stop here. Okay. Start, open the process of understanding. Let your brain start to function. Now, constant distance r from a straight line AB. So let me just draw the straight line AB here. Okay, guys. This is A and this is B. Now, constant distance from a line. Hello, hello, hello. From a point, we knew what it was. It was a circle. From a line, oh, this is a slightly different. When I say from a line, that means it must be perpendicular distance. Yes or no? This is a possible value of P, constant distance R, or P could be here as well. R, or P could be here. Again, R. The P double dash is another point here. Okay. So I'm making these points darker. Or it could be on the other side as well. Oh yeah. P triple dash. Or P triple dash. This point will be here. Are you with me? So when I connect these points, what do I get? What do I get? A straight line. I connect this point, what do I get? Oh, wow. So how do you describe it? Is, yes, a pair of lines parallel to AB. Do you see the parallelism? Yes or no? Parallel to AB, which is obviously which are these two lines are at a distance bracket में लिख रहा हूं perpendicular. Distance R. Now this distance R is this distance. R from AB. From. So the locus of the variable point P is a set of points, variable points, which are at a fixed distance R from this line. When I connect these points, I get a pair of parallel lines, one on each side of AB, one on each side of AB. So what do we understand? We understand there's a line on top and a line at the bottom of AB. But the two loci has an upgrade as well. Okay, for years, teachers have been teaching this. There's an upgrade in 2017 and 18 and 2000 and 1997. The first upgrade came in 1997 from Cambridge and as a question, and then another upgrade came in 2017. So I'm going to give you the upgrades as well. The line AB, this is the answer to the required question. But there's an upgrade. Right now, I'll give you exactly 30 seconds to copy this. Don't construct this. I'll show you the actual construction. Just copy this as a diagram for understanding. Okay? And then I'll show you the actual construction. And the version number 2 or the loci number 2 will get an upgrade. Okay, so we have this already done. Okay, we have this done. A parallel, this is the one without the upgrade. This is what you need to understand, that there are two parallel lines. Okay, I'll give you two more examples with this to reinforce what I'm trying to say. Okay. Board number 4. In board number 4, we do the same thing again. And this is when the first upgrade came in 1997, and a paper one question, and it was easy for construction purposes. So let's see what turns out to be. This was the line AB. Guys, how do you construct it? Well, you take your compass. Now let's take, for instance, this is the line AB. This is the line AB, correct? It's already drawn, and the requirement is to create locus of points with a 3 centimeters from AB. 3 centimeters, 3 centimeters from AB. So how do you construct it? Okay. You take your compass, you take your ruler, you take 3 centimeters here, okay, and you mark arcs, arcs, arcs. I'll show you how the arcs are actually marked. 3 centimeters, you mark an arc, 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 arc. Do it on both sides. Then you mark the furthest point from the arcs. Okay, now everybody knows how to make a 3 centimeter arc, right? You make a 3 centimeter arc, you mark the furthest point. Now, how do you mark a furthest point from the arc? Well, you do it here. You take the furthest point over here, mark the dots on the furthest points. Are you with me? Take a ruler and connect them. Do the same thing on the other side. Same thing on the other side. Okay? You mark arcs. No arcs, no marks. They want to see the working, obviously. You want to see the working. So this is what you do. This is still not the upgrade. This is the construction. Remember, locus is construction. You got to construct it. You did that. These are two parallel lines, one on each side of AB. The line AB was here. Yes or no? Line AB was here. You constructed the arcs. You took the furthest points. You marked the points and you connected those points together. This is how you construct two parallel lines, one on each side of AB. If you knew the theory, then automatically you will know how to do it. Any question? Great. So now this is not the upgrade. The upgrade comes after this. Be very careful. What has the examiner sought? Is he asking for just two lines? Or when you go to the edge of B, the last arc that you made was here. What happens after that? Well, after that, this turns out to be a semi this turns out to be a semi. So you go to the last point and you mark the arc again, and it turns out to be a semicircle. So the actual question finishes out here. This is the upgrade. This is the upgrade. Now, there are two examples that Cambridge did, and over 90% of the students attempting the 1997 question were not able to do it correctly. I will give you that example. Kids knew that they were supposed to make parallel lines. They did so. They even showed the arcs. That's fine. That shows you've done an honest job. But they didn't mark this edge. And they didn't mark this edge. This edge is also part, because when you go here, this becomes a point. In the locus number 1, that point made a circle. In this scenario, it will be a semicircle on this side and a semicircle on this side. Again, the distances are. Again, the distances are. Remember, the distances are. Remember, the distances are. Okay. Do you understand what happens? This is the upgrade. This is board number 4. I will allow you to copy this. Now, take your 1.5 or 2 minutes and copy this. Remember, if there are no arcs, your arcs are very important. Your dots, the extreme points are also important. And you connect those points. It's very easy. Just make a little bit of effort. You know how to use the compass. Because if you're a 13 plus, you should know how to use a compass. Remember, we are doing 2 dimensions, no 3 dimensions. 3 dimension is not in the new syllabuses. Remember the line that you draw, AB line that you had drawn, maybe it would be like, say, 7 or 10 centimeter long line. Okay, that's fine. But you draw it like that. Now, the upgrade from this is really amazing. This is partial of the upgrade. My giving you 2 examples would reinforce the concept. So I need to. My giving you these 2 examples would really be helpful. Okay? So please concentrate on board number 5 and board number 6. You can take a picture of this and keep it with you. So we're going to board number 5 now. Board number 5. The gaps for you recording is because we are recording. So board number 5, please, because of recording purposes, I did not allow you that much of time. You can always pause this video and do your construction easily. Remember, this is for your betterment. Doing it hands-on is better. Doing it hands-on is better than not doing it. Okay, so while I'm doing it, I will keep on recording this lecture for you people. I'm on board number 5 now, and this is the upgrades of 1997. The question was something like this. This is the outline of a house. Okay. The actual house had a playground entirely like this. Okay. This is the house, and this is the compound engulfing the house. Okay. In the 1997 paper, they said the owner of the house wanted to plant a tree. This is 10 meters by 5 meters. Okay. The owner of the house wanted to plant a tree 2 meters from the house. So what students did was they went here They marked arcs 2 meters. Took the extreme points, picked up their ruler, connected these points like this, and they got a region where they could plant a tree. They got a region where they could plant a tree. Now, 90% of the students who had done this did not do it correctly. So after that, this is not the right answer. Why? Because in this house, the line is fine and this line is fine, but this edge is a point. When you go to a point and you mark an arc, you always make it circular. Always make it, and that's the problem. This region is incorrect. This is more than 2 meters from this point. Do you understand? 2 meters, 2 meters, 2 meters, but this is more than 2 meters. This is not the right solution. It was supposed to be till here a straight line, till here a straight line, and after that it was supposed to be curved. So this is the correct answer. I hope you guys understood what I'm trying to say. When you reach the edge or a point, it has to be circular. It has to be circular. Great. So don't ever make this mistake. This was the 1997 paper 1 question of 4024 syllabus, and the latest questions and upgrades have also come in the 053 syllabus. Board number 6 will give you another example. Board number 6, I'm giving you another example. Okay? This is board number 6. Board number 6 is another example which came in the late teens year. Board number 6. This was a barn. A what? A barn. The barn had a railing. I'm going to draw the railing with red marker so you guys understand it. Had the railing from here to here. Okay? And on this railing was a chain. And a dog was was tied to this through a leash. And the dog was supposed to protect the barn and its main gate. And its main gate, or something similar to this. So what Cambridge did was they asked the students to construct the possible positions or the region where the dog could protect the barn. So the railing, which was continued all through the length of the barn, are you with me? The dog could be here. You mark an arc, say it was 3 meters or 4 meters of. So they marked arcs. The students marked the arcs here. But they went to this edge and they forgot where all the dog could go. It made it like this and like this and stopped here. No, this dog could go till here and could go till here. Correct? Correct? The arcs. But what about this? Oh, this is supposed to be curved, not just till here, but till here. This dog's leash could go right up till here. Not a square, but in circular motion at say point X. At point X, the entire dog could cover the gate of the barn. This was the gate of the barn. Okay, so was he able to protect the gate? Yes, because he had a 3 meter leash. A 3 meter leash. A 3 meter leash. So the red marker shows where all could the dog control. It could control till here. And in circular, all this region. This shows your concepts are clear about the edge of the railing. The edge of the railing X was able to cause him to go in a semicircular region here. So this entire region is what the dog could protect right till this edge Y. Just like the previous question, obviously the dog can't enter the barn, but yes, he could have probably entered this region as well inside because he's got enough places. So at night, he could probably sit inside the barn. If he hears something, he can go all outside, and that's the beautiful thing. If it's 1 meter or 1.5 meters, then he could have done another 1.5 meters here. So this entire region is what the dog could have control. Are you with me? So try to understand the beauty of this concept. It's X and Y. Once you reach an edge, it's not just a straight line. It's not just a straight line. Then it becomes circular. Then it becomes straight. You go to this edge, again it becomes circular. If there was no gate here, the dog could have easily reached another 3 meters like this, straight, and 3 meters like this. So this is how the railing, the ring was able to slip, and the 3 meter leash was able to allow the dog to cover this region for security. Did you like the concept? I hope you did. Because this is the ultimate, and they don't go tougher than this in Cambridge anymore. Thank you. So this is again the same part. I would advise again for my students to take a picture and keep this in their head, because you guys are more on visuals than anything. So don't forget, this was the first case where we constructed, we actually showed the construction. The edges were circular. Then we went to board number 5, where the 1997 concept came in, and this was the house, and the dog could, and the tree could be planted anywhere on this edge. Not here, not here, not here, not here. He says 2 meters. The tree was to be planted 2 meters from the house. So this is the house, and of course, you're not going outside the compound of the house. Why would you plant a tree outside the house? Why do you plant a tree outside the house? So you would be planting your tree probably here, 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 or here, or here, or here, or here. Not going outside the house, you're not allowed. And then board number 6 was the last part where you had a dog tied to a metal railing and was able to slip. The ring was able to slip. And where could the dog protect the barn? Well, the dog could protect the barn all through this railing area. Okay, it's a semicircular region here, a straight region here, and a semicircular. And if there was a door here, the dog could even enter inside. Do you understand? Do you understand this? This is very important for you to understand. Yes, you will be able to complete all this entire region. So least complicated, make it less complicated. Do you understand this? If there's no entrance to the door, do you understand this? This region of the barn is totally protected by a railing, a 3-meter leash, and a dog. Okay, good, great. So I'll allow you guys to absorb this concept. One question came up. If there is no door, if there is no door, the dog would obviously be here. If there is a door here, or if it's an open barn region, you can just go till here. You can even go inside. If this is an open barn, you can even go inside. So to less complicate things out, are you with me? It acts like a circle, right? So if it's not like that, then if there's a barn is not open for the dog to enter, then this is the region where the dog is able to be a security. Okay. Thank you very much. Next is number 3. We're going to move to board number 7 now for the third part of LOCI. Number 3. Locus number 3. First one we've done is distance from a point. Second one, distance from a line. And now the third one is the locus of a variable point P, which is at equidistant from two given points A and B is. So how do we understand this concept? What is he talking about? The locus of a variable point P, which is equidistant from two given points. First, make 2 points. Let's make 2 points. 1 point and 2 points. Don't make them too far off the. So 1 and 2 points. Equidistant. Now let's understand the theory before we go on to the solution. Equidistant means obviously something that is somewhere in the middle of these two. Okay. So it could be this point, correct? Yes or no? A little further off, it could be here, here, another distance, correct? But of course, equidistant. Or it could be further away, somewhere here. Or could be here on this side. The double dash triple dash, fourth, or could be here fifth. So when I connect these points, what do I get? Perpendicular bisector. Perpendicular bisector of line AB. Now remember, AB wasn't a line, but you sort of made it a line. How do you construct it is the easy part. Yeah, that's not too tough, but you need to remember this. Anytime they ask you to do a perpendicular bisector, this is what you need to do. Okay? Even in transformations, there's something called the perpendicular bisector that comes in. And you need to know this as like the back of your hand. Okay? So how do you construct this? Well, it's much easier than if you take 2 points, A and B. You connect these 2 points, correct? You pick up your compass, spread the compass to a position that is greater than half. Now, if I have a point here, this is half. This point is half in between A and B. You take a point which is more than half, and generally we don't say you have to go exceed there, no, you just have to be more than half. That's the condition. Can it be more than AB? Yes, it can be more than AB, but I don't advise that. I would do something like this and mark an arc up and one mark arc down. Same length, don't remove the compass length and mark an arc here. Basically, it looks like this. Okay, something like this. You take this point and this point. Actually, it's a marker color, so you understand. Connect, take a ruler, connect these 2 points together. Congratulations. This is the perpendicular bisector of AB. The perpendicular bisector of AB. There is no other thing required here. It's that easy. It's called the perpendicular bisector is the perpendicular bisector of line AB. Okay. So this is number 3. This is really easy. You don't need to worry too much about this one. Okay. So I give you like 1.5 minutes right now to construct this. This is a theory. It should be somewhere in the middle. I looked at it. It looks like the perpendicular bisector. This is not the construction. This is the construction. This is the construction. Remember, no arcs, no marks. So take your time, take a picture of this and record it. Okay. Do the construction yourself. Do not forget, that's the easiest one you get. The third one, the fourth one is number 4. The locus of a variable point P, which is at a constant distance which is which is sorry which is equidistant from two intersecting lines is, now first of all we take two intersecting lines. Okay, we take two intersecting lines. Okay, two, we take a line like this, we take a line like this, intersect at say x. Okay, now this is, you need to follow this really carefully. This is slightly more complicated, but your queries will be solved while you do hands-on. Okay, all you have to do is have a good strong compass. A strong compass means not one which is loose, because if you make a mess here, then your answer will be incorrect. So what do I do? Two intersecting lines. So you want something that's equidistant from these two lines. Distance from a line has to be perpendicular distance. Yes or no? Yes or no? Yes or no? Yes. So this point would be equidistant from two lines. And another point here somewhere should be equidistant from this line. Okay, copy? And when I connect it, I get something like this. So this is the line. Okay? From two intersecting lines. So this point of intersection was X. Two intersecting lines, say equidistant is this, these points. Okay, this line or this line. So it's equidistant from here and here. Okay, and from here and here, equidistant. And from here and here, equidistant. So for theory purposes, this is how it's done. This is how it is supposed to be. But when you actually start construct it, when we actually start to construct it, it's slightly, it should be on board number, that's board number 7. Am I right? So this is board number 8, and we're going to construct this right now. Okay. Board number 8. LOCI number 4, board number 8, you need a good strong compass, you need a ruler, and you need to know those lines. Okay. Say for instance, these are the two lines. Okay. Line number 1, line number 2. This is your point of intersection called X. I will make you grow up, mature up a little bit as you go ahead. This is what you're supposed to do. Now follow these instructions really carefully. Okay? Follow the instructions really carefully. You take any distance on this compass and make sure the compass is not a shaky one. Okay, you mark an arc here, from here, go here, mark an arc, go here, mark an arc, right? So, it's the same distance. Okay. After that, you take your compass again and you mark. This is really interesting. So should it be the same length? No, not necessary. But whatever length you take now also stays fixed. So you fix out a length, say just take any length, say this length, okay? You go here, go in a space, and you mark an arc. You go here, in a space, and mark the arc. It's very, very visible here, so you won't have a problem. This arc and this arc intersect at this point. You just need this one point. You already have X. And if you want, you can do the same thing again here. You go here, mark an arc, mark an arc. You do your first arcs. Go to these arcs and mark in space, this space. Go to this point, mark in space. So this arc now is this arc, and this one is like this. Again, you have another point. So you don't really need this, but for practicing purposes, I got you to do it again. I start again, one arc here, one arc here. Take another length, any length, fix it out. Mark an arc here, mark an arc here. Go to the other side if you want to. Tuck, tuck. Fix out a length, tuck, tuck. This length and this length has to be same. This length and this length has to be same. Okay? All four lengths don't have to be same. Only A and B has to be same. C and D has to be same. Not all four have to be same. But just for simplicity purposes, mark an arc here, mark an arc here, any length, same length. Now, A's distance from this arc and B's distance from this arc remains the same. You mark an intersecting point here, here. You've done it on the other side as well. Here. Take your ruler, connect these 2 points. And the ruler on this side, you find out, wow, what accuracy. What accuracy. Extend this line wherever you want to go. This is the perpendicular bisector. It is the perpendicular, it is any point on this line is equidistant from this line L1 and line L2. Okay, equidistant from line L1 and line L2. Okay, congratulations. This is, and the word for it is angle bisector. Angle bisector. It's called the angle bisector of L1 and L2. Why do they say angle bisector? I'll just show you. This is your protractor. You go here, roughly, check the angle here. This angle is 10, 20, 30, 40, 45, approximately 44 degrees. Approximately 44 degrees. So this angle turned out to be, for example, is 44 degrees. When you go and check this angle, you find out, wow, this is 10, 20, 22 degrees. Perfect. This angle turns out to be 22 degrees, half of this. That's why it's called the perpendicular, it's called the angle bisector. It's called the angle bisector of L1 and L2. I know this is slightly mature, but I give you, keep repeating and practicing on your own in real time, and you'll be able to do it really well. Okay, so I'm going to do this once more for you, board number 9, once more for you. to make things easy, okay, once more for you, board number 9 is a reinforcement. You have a line L1, you have a line L2. You go here. For your record, before you start the question, just check this out. 60 degrees, correct? One of my students asked me, uh, it's really important question. So if I know this is 60, why don't I just draw 30? No arcs, no marks. No arcs. So if you just construct a 30-degree here, you're cheating with the examiner. He doesn't want you to do that. Okay? This is your line 1, line 2. You're going to pick up your compass. You're going to go here, mark an arc, same length. Go here, mark an arc, connect this to this, and extend it. This is your angle bisector. Or in simple words, any point on this line is equidistant from line 2 and line 1. Line 2 and line 1. Any point, perpendicular distance is the same. Perpendicular distance is the same. So it's that easy. Okay, one arc here, go here, mark an arc, go here, mark an arc. And you have this line straight. Now, surprisingly, because I need to open your perspective and your thinking, remember one thing. This can happen here on this side and this side. Yes or no? As well, right? Correct? But what about this? Can we have a line like this? Yes. This is line 1, and this is the other side of line 2. So we're going to go here, and do the same thing here and here. Do the same thing here. And so this is this is rule number 4 of LOCI. It ends here. So it starts with this, number 4. Then you go on to this. Board number 8 shows you the actual construction. Board number 9 is reinforcement. Will give you 2 lines, bisecting lines. Okay. So anytime, well, the Cambridge hasn't asked you ever to do 2 lines bisecting. They normally give you a region where you have to region inside this space where they ask you to draw the angle bisectors. So you just do it like this. That's all. Okay. So don't you worry. That's how easy it is. So the answer to this entire question, the locus of a variable point P, which is equidistant from 2 intersecting lines, is the angle bisector of the 2 lines. Is the angle bisector of the 2 lines. That's how you write down. Angle bisector of the 2 lines. Okay. I have taken the pictures of all these, so you will not be. You can receive it from me or ask me to inbox you. I will send it to you. Thank you. Now we're going to be doing number 5. Rule number 5 says the locus of a variable point P at which a given segment, given segment at which a given segment of a straight line AB subtends an angle X. Subtends an angle X is. Now, if I take a long segment AB, don't you guys confuse yourself. Subtension of an angle. Subtension is geometry, laws of geometry. Okay. Subtends means opens up. If you have a circle, if you have a circle and a line AB, now this is not a diameter, huh? Line AB subtends an angle X. Remember there was a law that says angles in the same segment must be equal. So subtension means opens up. So if an angle X is opened up, this is not there yet. Okay, subtension means opens up. And that angle again opens up another X here or another X here. So it's P, P dash, P double dash. Subtends means opens up. Subtends means opens up. So the angle in the same segment must be equal. There's a law of geometry that says angle in the same segment must be equal. That is only possible if this was part of a circle. This was part of a circle. Angles in the same segment must be equal was a rule of geometry with circles. This was your line segment. I'm going to mark it with blue. A line segment marked with blue. It subtends an angle X, X, X. This line segment opens up an angle X here at the circumference of a circle. Okay. In the same segment, all the angles are same. All the angles are same. So this means what? X, X, X. All three angles are same. All three angles are same. So if the angle opened up here is X, can it not be on the other side as well? Can this angle X not be on this side? Oh, yes, it can. So what does this mean? This means that this arc, which was part of a circle, and this arc, which is also part of a circle, remember these were part of a circle. Only if they are equal will A and B, the line segment, open up the same angles. Say, for instance, 60 degrees, 60 degrees, 60 degrees on this side, and 60 degrees on this side as well. The only condition is this arc and this arc, these two arcs must be congruent. Congruent means equal, exactly the same. So the locus of a variable point, now listen to this question. Locus of a variable point at which a given segment of a straight line AB subtends an angle X is a pair of congruent arcs, one on each side of AB. This is the solution. Pair of congruent, pair of congruent means same size arcs. Same size arcs. The pair of congruent arcs, one on each side of AB. So from here till here, I'm underlining thoroughly. There's a pair of arcs, one on each side of AB. Okay, so if there's one angle X on top, an equal angle can be drawn at the bottom. This is also angle X. This is also angle X. If this is 60 here, down here, it could be a 60 up there as well. For the 60 to be up there, AB has to make two congruent arcs, each of the same size. Each of the same size. One on top and one at the bottom. That's law number 5. Law number 5. Please copy. Now we're going to go to law number 6. It was board number 10. Okay, board number 10. I've taken a picture. Remember, all the boards can be, all pictures can be taken from me. Now we're starting board number 11, rule number 6. The sixth law says that the locus of a variable point P at which a given segment of a straight line AB subtends an angle, subtends a 90-degree angle is, put your pens down, everybody, and concentrate here. If you want a 90-degree, there's a law of geometry that says if you have a circle, if you have a circle and AB is the diameter, it will always subtend a 90-degree. This is already known to you people. So if this is AB, it will be this point. When I connect these points together, I get a circle. And AB must be the diameter. This is what it says. Locus of variable point P at which a given segment of a straight line AB subtend means opens up a 90-degree, okay, is the answer to it is very simple, is a circle is a circle with AB as the diameter. Construction is not required. It's very easy. Everybody knows how to make a circle. Everybody knows how to make a circle. Construction is not required here. Theory is required. So you guys should copy this immediately and learn it. So if you have a 90-degree subtension, always remember it's a circle and AB is the diameter. Or it's a circle with AB as the diameter. That's board number 6. Board number 7, but that's rule number 6. Rule number 7 is the last one. Well, you don't need that rule number 7 anymore. It's not part of the syllabus. So we're just going to just leave that as 3 dimensions. So 3-dimension loci, 3-dimension loci is not included in this lecture because it's not part of the syllabus anymore. However, if anybody requires it, please inbox me. I will send you a recording of 3-dimension loci if it's required. Cambridge doesn't require you to do 3-dimension loci anymore. Thank you very much. I hope you enjoyed this lecture and I hope you learned something from it. Thank you very much. Assalamu alaikum.